Hey, everybody. Another morning episode of the THD Podcast. And today we've gotten up early so that we could have a special guest coming to us from Seattle, Mr. Tim Whitwell from Tectonic Audio Labs. And of course, always to ask the technical questions as we have Simon Weston joining from Japan. So, hey, everybody, how you doing this morning or this afternoon, Tim?
I'm doing great, thank you. Yeah, nice to see you, Dave and Simon.
All right. So yeah, Tim's running engineering at Tectonic Audio Labs in Seattle, which has a pretty deep history in flat panel acoustics. Now, Tim, can you tell us a bit of the origin story about where this technology comes from?
Absolutely, yeah. So actually the whole concept of kind of using bending waves for audio originated with the Ministry of Defence in the UK in the sort of mid-1990s, and they were actually trying to make fighter jets and helicopter cockpits quieter. Oh. And at the time, this was when composite materials was a fairly new phenomenon. So this idea of taking let's say two skin materials and putting some lightweight core in between, like a honeycomb structure or so on. That was a fairly new field, and obviously big applications in things like Formula One, aerospace, and so on for making plane parts and all that are light and stiff. And what they thought was that these composite materials might absorb some of the sound energy that was being generated in the cockpit. And actually what happened is it got louder. And they realized that these panels they put in thinking it would absorb the sound, they were actually taking the structural vibrations of the airframe and turning it into, amplifying it into sound. So the actual Ministry of Defence work wasn't obviously going in the direction they wanted, but they saw there was a commercial opportunity there. And so there's a division of the Ministry of Defence in the UK. There's a division called Kinetic, and their job is to essentially, commercialize defence technologies. And so they were looking for a company to basically run with this. And so a group of hi-fi companies in the UK that came under what was called the Verity Group. And so these are famous hi-fi brands like Quad, Mission, Wharfedale, so on. So that conglomerate, they acquired the IP from the Ministry of Defence. And then they set up this little R&D company called NXT in, I think, late 1996 was when it was officially formed. And then I joined as one of the kind of early physicists in 1997.
Wow. That's quite the journey then. So do you have something to add, Simon?
You just mentioned generating sound with bending waves. Could you just contrast what that means as opposed to, a classic speaker?
Oh, good point. Thank you. Yeah. So we're all used to a conventional speaker that produces sound. It's designed to be used as a piston. So, the cone structure doesn't deform, it just remains as a rigid cone and just moves backwards and forwards, essentially driving pressure waves into the air. Whereas something that's operating with bending waves, there are actually waves that travel through the material of that diaphragm, whether it's a cone or a flat panel. It happens in a cone anyway. Eventually, you get to high enough frequency, it happens. But it's always something that's it's been a little bit of a mystery. And of course, when you start talking about bending waves traveling in materials of a finite size, then you get what's called modes, right? And again, something that the acoustic engineers have traditionally kind of run the other way from. When you see a mode, oh my gosh, it's a mode. And again, mostly because it's poorly understood. And this is where that work that NXT did. Again, NXT had its issues, and we all accept that. Obviously never quite made it. But in terms of doing some of that fundamental research and development to exploit the bending waves and the bending wave resonances, they had a team of probably, at least 40 mathematicians, physicists, and engineers all working on this problem for a good, 5 years or so, just to understand how the bending waves, how they work, how do we model them, how do we optimize them, and how do we make good speakers from this. So there was a big mountain to climb in terms of understanding this new technology. I say new, but in terms of it's never really been exploited for audio before. The basic concepts were extensively researched during the Cold War, because it governs how things like submarines produce sound, for example, as they travel through the water. And so a lot of work was done on those shell materials and how bending waves are excited and travel through sort of materials by a lot of the naval research bodies and stuff around the world. So, some of the fundamental math was done. I mean, originally the math was done by Lord Rayleigh back in the 1800s. And then one of the famous female mathematicians, Sophie Germain, she provided some critical corrections to some of the equations that were not quite there initially. So that there's a big body of mathematical research behind the concept, and then there's this body of kind of work done by the naval laboratories and during the Cold War and so on. And then you get to essentially what NXT did specifically in the field of audio.
Interesting. Now you kind of touched on the fact that the distributed mode loudspeakers from NXT, it was never a huge commercial success. There still are some pro applications for that, but I think one thing that's kind of key and where Tectonic has led to is transitioning to putting that into drive units, which you call the balance mode radiators, the BMRs. Yeah. So basically, what were some of the fundamental reasons obviously commercial success was the goal, but tell us a bit more about that transition from DML to BMR.
Yeah, really good question. Yeah, so obviously the original technology that NXT worked on was, as you say, DML, which stands for distributed mode loudspeaker. And the idea is to take a large format flat panel structure and excite it in such a way that it has lots and lots of modes across the audio band. I mean, typically dozens of modes are desirable. And to really make something like that work, it needs to be quite large, at least, A5, A4 type size would be a good starting point, just so that in a structure of that size, you get enough of the bending wave modes to really give you the benefits that the technology genuinely provides. But of course, one of the issues is that, the way that you, to get the maximum modal density in something like that, which is what you're looking for, there are certain constraints, right? You have to hold the panel in a certain way. You have to excite it in a certain way. And some of those constraints mean that it's perhaps not ideal for going down to the lowest of frequencies in the most efficient way. Mm. And again, and a good example of that is the DML product that we currently make, the DML 500. It's a single flat panel. It's about 600 millimeters by 400 millimeters. So a pretty large object. And, it operates from 100 hertz to beyond 20 kilohertz. Single transducer, no crossovers or anything like that. But again, as you go to the lower frequencies, you start to, you want to have different boundary conditions. You want to have, a nice soft roll surround so that the panel can move a lot of air at low frequencies. So that was obviously one of the reasons why. But also, every time we spoke to a customer about implementing the DML solution, it was always, this is how you have to hold it. This is how you have to constrain it. And, it felt like having a drop-in solution like a drive unit, in a basket that can just be screwed in, away you go. You can do the low frequencies like a regular speaker where you have a port or a passive radiator or seal box. But it would be, the idea was it'd be nice to have something like that. And so there was a whole kind of side of research that went into how do we combine, the benefits of DML with a conventional type piston speaker at, drive units at lower frequencies. And really what we came up with and what BMR is all about is actually something that's quite a bit more special than just taking those two things and putting them together. In trying to do that, we actually discovered something quite a bit more beautiful in terms of the maths and the physics behind it, which is what BMR is. And so you can loosely describe it as a combination of a pistonic drive unit at low frequencies with some modal behavior at mid and high frequencies. That's a very, very loose description. It doesn't really truly describe what the BMR is doing. And hopefully we'll get onto that at some point. But
okay.
Can we just back it up for a minute and just say, you've mentioned a few times the benefits of DML. But can we actually just go through what are the benefits? What's the underlying guts of the whole thing?
Oh yeah, no, thanks Simon. Yeah, so with the DML, so what, as I was describing, we had this large format panel radiator, and basically we cover 100 hertz to actually beyond, we go up beyond 25 kilohertz even, with a single object. So there's no crossover. And this is one of the great things, right? It's one of the most detrimental things to speech intelligibility, and actually getting a smooth response from your speaker into the space around you, is the crossover. And unfortunately, the physics of drive units, conventional drive units, dictates that crossover typically has to be somewhere between 1 to 3 kilohertz. And that's the worst place you'd put a crossover, because if you could choose where to put your crossover, you go, well, definitely the 1 to 3 kilohertz region is out, because that's where the human ear is most sensitive. So unfortunately, with the conventional technology, you're forced to have a crossover in the worst possible place. And of course, there are many, there's lots of, very great technology, measurement systems, simulation systems, and very talented engineers who do a fantastic job. But they're still kind of plastering over the gaps a little bit. So one of the key benefits of the DML is that we can cover that whole range without any crossover. The second one is that we're doing it with a single acoustic source. So we don't have a tweeter here and a mid-range here and a bass driver down here. That when you're looking at that at a distance, you're going to get some interference effects from all of those, especially around the crossover region, no matter what you do with your crossover. So again, having a single acoustic source theoretically gives you better timing. But I'd say probably the biggest thing that really kind of freaks people out when we talk about it, is the fact that the radiation coming off the DML is predominantly diffuse in output. And this is something weird. And again, you see go to like a recording studio or concert halls, and you'll see on the wall, you'll see these kind of funny rippled patterns on the walls, right? Like the eggshell cartons that people do at home when they're trying to do this stuff. And essentially what that's doing is that's what's called a diffuser, and it's essentially breaking up the reflections. So what you get with a normal loudspeaker, what we'd call a coherent radiator, you get the direct sound waves coming off the drive unit, and then when you have a wall nearby, for example, you get a reflection off that wall, and that reflection then meets the original outgoing sound, and the two sources interfere, and they either interfere constructively and they sum to give a more output, or they cancel out, they interfere destructively, or somewhere in between. And that again creates kind of hot and cold spots in the room at different frequencies, different positions. What we find with the DML is, because it's vibrating at a very, very kind of complex vibration pattern across the surface, the sound coming off it is actually predominantly decorrelated and diffuse. And so what that means is, when you get the original signal meeting the reflection from a wall, they just kind of pass through each other. There's no strong interaction. And of course, that then leads to someone to say, well, how do I get a stereo image, for example? If there's no coherent information coming off, how does that work? How do I pinpoint in space where the sound should come from? And again, this is something really key to DMLs, is that you have this initial very, very sharp transient spike that comes from the initial deformation around the region where the transducers actually push on the diaphragm, on the big panel. There's an initial deformation there, and that sends out this initial kind of coherent, very, very short coherent pulse. There's almost no overshoot. It's really, really fast. And then what follows that is what we call the diffuse tail, and that's all of the diffuse energy from the modes vibrating in the panel. Now again, of course, people say, oh well, then surely that must sound like it rings, because it's delayed, right? But again, you look at the impulse response, and you'll see everything arrives, the initial transient and all the diffuse energy all arrives within about 9 milliseconds. Okay, so there's something called the precedence effect. Precedence effect essentially tells you when something is an echo and when it's not. So what it says is, if you have a sound and then you have another sound, and they arrive within this time window, you actually don't perceive them as two separate sounds. You just hear it as the original sound being louder. But if that second sound arrives outside of that window, then you hear a second sound. So that window depends on the spectral content, but typically it can be anything from 30 to 100 milliseconds. So when we look at the DML impulse response and we see everything arrives within about 9 milliseconds, regardless of what your signal spectral content is, that's all going to be perceived as just the original signal just sounding louder. And that's...
Is that a little bit to do with, like, comparing that to a traditional speaker with crossover? Is that just because some of the signals are moving at different paces, so that's why you can have this cancellation effect, such as a mid versus a tweeter, or two mids? Are they creating cancellation effect, or is that kind of one of the issues?
I mean, all the signals are traveling through the air at the same speed,
okay,
regardless of frequency. So the air is a non-dispersive medium in that sense. So but you have a time of flight difference from your mid-range drive unit and your tweeter, which are separated in space. Okay, there are some designs that you have like a coaxial, where they mount the tweeter inside in the middle, which again, that can be great. But again, there's still a crossover somewhere, and so on. But yes, those signals have to travel at a finite speed, and coming from different sources, they get there at different times, and so they have different interference effects. Yeah.
Interesting. Okay. Any more on DML you want to discuss there, Simon?
I'm just curious. You mentioned DML 500, and you said low frequency. 100 hertz up to whatever, basically. Is that an open baffle? And is the fundamental actually the first bending mode, or does it have a pistonic mode and then a bending mode?
Yes. So that is the actual size. That's not in an infinite baffle or anything. It will produce good output down to about 100 hertz. We recommend crossing over to a subwoofer somewhere around about 100 hertz or so. I wouldn't tend to recommend much lower than that, but that's about the right sort of region. And yeah, absolutely. As you go, I think the modally active is probably above about 300 to 400 hertz or so. So below that, there is some kind of pistonic type motion for sure.
So then you actually have a flexible flexible surround, so you get a pistonic mode essentially at the lower end, and then it just starts to go into the higher modes.
Yeah, so it's not as flexible as a typical roll surround, and again, this is the reason why we're saying you could drive it much lower. I mean, we could put a more flexible surround on, but then that would adversely affect the DML properties which is what we really want out of it. So again, we say, run it down to 100 hertz. And again, you can put a lot of power into this thing. I mean, you can put, I think continuous is like 400 watts or something, with peaks of, we've had it running with peaks of over a kilowatt. So, two of those DML 500s will cover, a good 300-400 seat, maybe even more. Actually, no, maybe even up to 800 seat type arena. Or theater, for example.
Yeah, actually, they had them at the ISC event in Amsterdam this year. They had them facing in the Tectonic booth, and literally had people coming from down the aisles wondering where that sound was coming from, because it actually comes off the front, but it also spits out the back, because of the nature of the construction, I guess. So,
we call it a diffuse dipole.
Wow. Okay. So we kind of discussed where the technology comes from, and now the BMR is kind of the transition into the commercialization, and it's going into a lot of different devices. Smart speakers, soundbars, automotive is a big category, and some of the aspects you talk about being full range is one of the kind of critical commercial aspects in deploying the BMRs. So maybe before we get too much into the commercial, sort of stop myself, but maybe we could kind of go through some of your slides into kind of explain the diffuse nature, and then we can circle back and kind of discuss like how these are applicable in speaker applications such as automotive, etc.
Perfect.
Yeah.
Shall I call up some slides?
Please.
Here we go.
So the BMRs are built in the format of a traditional cone loudspeaker, but it's not that, right?
Absolutely, yeah. It's built on the same production lines. Very, very little change needed. I'd say probably the only difference when you're constructing a BMR is the fact that we don't have a hole in the cone in the middle, where you'd normally assemble, either from the front or the back, and then you put your dust cap on at the end. We obviously don't have that. There are about 2 or 3 ways of building it with depending upon, perhaps they all have kind of pros and cons, but they all can be done in, and are being done in extremely high volumes with the typical kind of reliabilities and so on that you see for normal speakers. So there's no real difference there in that sense. And actually, what you can see from the slide I've got just on my introductory slide, there's a sort of cutaway image there of a BMR. Couple of things to note, I suppose. Apart from the diaphragm, every other component that's in there is the same as what would be used in a normal drive unit, a conventional drive unit. Magnet, steel cup, steel pole piece, voice coil wound onto a former. Former could be a conductive former, aluminum, or it could be glass fiber or so on. A spider, a roll surround, and that's it. And so the only difference really is instead of a cone-shaped diaphragm, we're using a flat composite material there.
So the NXT panels are generally all rectangular, and the Tectonic BMRs are circular. Does that make a lot of difference in terms of the generating the diffuse field? It's just a different set of calculations, or what's the contrast of those two?
Yeah, so I mean, we don't really talk about the BMR as being diffuse, certainly not in the same way that the DML is. Certainly, our measurements show there is a degree of diffuseness from the BMR at the higher frequencies, but it's nowhere near as much as the DML. And the reason for that is the DML has dozens, if not hundreds, of modes across its audio band. The BMRs typically have 3 or 4 modes. So it's not as predominantly diffuse radiator like a DML. It just has a little bit of perhaps of that character, but its core benefits lie elsewhere.
So this thing about the number of modes then is basically related to the speed of sound of the material and the dimensions of that material essentially. So a BMR is just not large enough. Yes.
Well, again, actually, really, what it comes down to is, and what I should do is really tell you what a BMR is, and then that will make more sense. So perhaps if I go at it from that angle.
Yep.
But what you say is absolutely right. I mean, it's a function. The number of modes in a given sample is a function of the size of the sample and its material properties. Exactly. But yeah, let's come at it from a slightly different angle for a moment, if that's all right.
Please.
So really, just to start off. So really, what I'd like to do is to just kind of very quickly review the limitations of conventional pistonic type drive units.
Yes.
And again, I'm not going to go through the whole presentation here. I think your listeners might get tired after a while, but I just want to capture a couple of key concepts. So there's these two key limitations for a pistonic drive unit. One of them is called breakup, and this is where the bending wavelengths traveling through the diaphragm material equal integer multiples of the dimensions. And what happens then is that your diaphragm, remember, in a piston type speaker, your diaphragm is typically a thin floppy material that gets its stiffness by being formed into a cone shape. It's like you can take a piece of paper and it's pretty floppy, but you roll it into a cone and you can put a bit of force onto it. The downside is that if I take that rolled up cone of paper and I'm pushing down on it and it's taking the load pretty well, if I just tap the side very gently anywhere, it buckles and crumples. And that's really what's happening when a cone breaks up, is that suddenly it stops being rigid and it kind of collapses. And so you get these really nasty peaks and dips in the response that are, totally in order, not nice to listen to. So that sets a limit between the size of a given drive unit and its useful bandwidth before it starts to go into what's called this breakup effect. Now, the interesting thing is that, and this has actually become more relevant in the last few years with some of the new technologies, even if you could solve breakup, even if you could push breakup out of the audio band by using some funky materials, right? And nowadays, you can get diamond coatings, you can get beryllium or beryllium alloys with copper and so on, all kinds of stuff. And there's even some graphene technologies as well. Now, even if you use these to make the diaphragm completely rigid, you end up encountering the second problem, which is what we call power beaming. And so essentially for your piston drive unit, there is a, and it depends on the size of the drive unit now, and it's basically where the wavelengths in air. So previously we talked about the bending wavelengths becoming of the same sort of size as the diaphragm. Now it's the waves in air becoming the same sort of size as the dimensions of your diaphragm. And when that happens, you start to get this, as you can see on the screen here, these kind of lobe type behaviors. So on the far left here, this is low frequencies. You see a nice 180 degrees of sound coming off your speaker. This is what you want. In most scenarios, you want to fill the room with sound. And again, at low frequencies, not a problem. But as you go up in frequency, as I say, you reach this limit, and that's where all of the energy starts to be concentrated directly in front of the drive unit, and off to the sides, there's very little. And you can see up here to the right-hand side, you see exactly that. So what we call on-axis, or directly facing the drive unit, there's still good output, but you just go 5-10 degrees off, and it's completely fallen away. And so again, this is not going to fill the room with intelligible sound, because there'll be no high frequencies anywhere but directly in front of the speaker.
And so, that's why the hi-fi fanatics have that little tape spot on the floor on their carpet, so they get what they call the sweet spot.
Exactly right. Exactly. That's exactly what's going on. And again, this is what's interesting, is that this power beaming thing wasn't such an issue. You know, I mean, you still needed to have multiple drive units anyway because of the breakup problems, and power beaming to an extent. So that's why you need to go from a big bass driver to a smaller. You need a big bass driver to shift the air, but then you go right. But that only works up to say 300 hertz. And then it starts to break up and it starts to do this power beaming. So then I need to go to a mid-range driver, which is quite a bit smaller. And then that works up to 3 or 4 kilohertz maybe. And then I need to transition to another smaller driver again to handle the high frequencies.
Can I ask you a quick question on power beaming? So would it be fair to frame it in these terms that the acoustic radiation, the wavelength in air from one side of the driver to the other side of the driver has put that completely out of phase, so it's sort of self-cancelling itself?
So everything we're looking at here is done in an infinite baffle, so we're completely separating what's coming from the rear side from the front side.
Yep, understand that. So the what radiation from, I don't mean from one side, I mean not from front to back, but from one edge of the driver across to the other edge.
Uh-huh.
Is it something like that? It's an acoustic cancellation effect.
Yes, absolutely. Yes, that's what's actually happening in the far field, is that you're getting path length differences. So you've essentially got, you know, your cones moving up and down, and basically this point here and this point here, at some point in space, there is a path length difference, and that path length difference is insignificant when the wavelength is very long at low frequencies, but when the wavelength becomes about the same sort of size as the cone, that's when that path length difference becomes important, and then you get these cancellation effects.
Do you get a constructive interference also then? So you actually get gain relative to low frequency in the beam?
Yeah, yes, you can do. It tends to generally be more cancelling than reinforcing, and again, you can see that from the curves here. And again, it's also important, and actually you bring up a really good point, Simon, as well, is another aspect to this is what's called the radiation impedance characteristic. So again, we're probably getting, you know, quite in depth here, but when you look at what's called the radiation impedance, and this is where different regions of the diaphragm effectively kind of see each other, and they're able to sort of communicate. And so, yeah, that radiation impedance for a cone type structure has a lot of ripple at the high frequencies. Not only does it ripple, but it also decays, and so you start losing output as a result, but also that output starts to ripple quite significantly. With a flat diaphragm, you don't get that. With a flat diaphragm, you get a straight line. So actually, a flat diaphragm, just looking at it from a radiation impedance perspective, a flat diaphragm is clearly the best solution for a speaker drive unit diaphragm. The problem is that no one's been able to realize it previously because of the problems that we're going to see about how you control the modes and so on. But yes, that comes in.
Perfect. Onward.
Okay, so moving onwards. So there's the beaming effect, what we call power beaming. So how do we solve it? Or let's put it another way: is there something out there that doesn't have these problems? And the answer is yes, in theory. So when you study, if you study acoustics or so on at university, one of the things that you'll study and solve the equations for, because they're relatively straightforward, is a flat circular disc driven by a perfect force. And actually, this is mounted in an infinite baffle for the moment. So by perfect force, I mean a force that has zero mass. All right, and we'll come back to that in a minute. But if I could take this flat circular disc and drive it in a way that, I don't have to touch the disc or anything like that, then that disc has these ideal characteristics. So firstly, it has flat on-axis sound pressure level. So that means directly in front of it, it's going to give you a flat response. But also, it has a smooth and extended sound power response. And the sound power response is really, really important. And something that actually at Tectonic, we seem to be sort of leading the curve in kind of, propagating this out there. So the sound power response is where you take a speaker. I'm going to use one of my props here. Take a speaker, and so what we call the on-axis response is literally just measuring directly in front of it like that. And that's the most ubiquitous measurements that's made of speakers. But what we feel is more important, so what we actually do is we measure 5-degree resolution from 0 to 90 degrees. So we actually have in our anechoic chamber, we have an array of 19 microphones permanently fixed and mounted in this kind of arc, 90-degree arc. And so we measure at each of those microphone positions around the speaker. So we then build up a full kind of hemispherical map of the pressure field coming off the drive unit. And what we do is we then integrate that all together, and there's certain weightings to do with the angle that you're at. But when you weight that all together, you end up with something called the sound power response. And it's sort of like it's almost like an averaged response of all of the energy that's being radiated into the room. And again, we feel this is really important. So just kind of going back to something we talked about previously. So, and Dave mentioned about the sweet spot. So you think about the way people used to consume their audio, right? In the olden days, people would typically have their speakers either side of the TV screen, and they would be sitting on the couch opposite, right? In that kind of on-axis sweet spot. But nowadays, hardly anyone listens to their audio like that. Most people, so let's take earbuds and headphones out of this for the moment, but anyone else who's listening to music, most people are listening to a smart speaker that's sitting somewhere on a shelf, on a kitchen counter, on a coffee table, and they're standing here, they're sitting here, they're at the desk over there. They're almost never in that what we'd call that on-axis location of directly facing the drive unit. They're almost always off-axis. And so that's why we've really pushed this sound power response as being much more representative of what somebody in the room is going to hear, because this is measuring like the total energy content of the spectrum of that energy that's being radiated into the whole space.
So that sound power response actually, regardless, even if you're on axis, it's still a critical measurement, because just like you were mentioning earlier, the room reflections, your air accumulates all of that anyway to get the audio impression, right?
Absolutely. And again, there's a lot of work by a famous engineer, Floyd Toole, where they talk about how the reflections from nearby boundaries, for example, ideally should be as similar as possible to the outgoing sound, to minimize any colorations and preserve the image and so on. And again, if you have a drive unit that has a nice extended sound power response, generally what it means is that it's the character is going to be fairly similar all the way around. And so what's coming off at 60 degrees and at 80 degrees and 45 degrees isn't going to be radically different and cause any major issues in those reflections. But what you're doing is, if you have that smooth extended sound power response, you're giving it the best shot in terms of how it sends the sound into the room, because we have no idea how people are going to put their speakers, whether it's in a reverberant, conference room with glass walls and a reflective table and very little kind of damping material, or it's going into a domestic environment where there's sofas and couches and people and so on. So again, your best starting point is to have something that has these properties of the smooth and extended sound power response. So just looking at the at the image here, and again, what I've shown on the right-hand side is that you can see a mode in the disc there. So you can see, we talk about a nodal line. That's the black kind of ring in the middle here, where it's dark blue, and the very center of that is a black ring. And then as you go to the edge, or as you go towards the center, it kind of goes to the red region again, which is a region of high movement. And so on the far right, you can sort of see what that looks like in cross section. And now you can see how the disc bends. But what's really interesting for this what we call this free disc, this circular free disc with the perfect force, what's really interesting is that it automatically arranges itself so that the modes cancel out on axis only. And so what they do is that the different regions of the disc arrange themselves so that the area that's moving in any one direction multiplied by the acceleration of that area is always cancelled out by what's moving in the opposite direction. So again, looking at this right-hand image here, so the inner region up to where you cross the plane, where the nodal line is, so the acceleration and area of this inner region is completely balanced by the acceleration and area of this outer region, and they're in perfect balance. And again, this, physics teaches you that this has to be the case. You have to conserve angular momentum, right? Again, this is for a free disc. There's no force going in at the moment. So if you don't have these conditions met, this thing will just start flying around in space. So you have to conserve your angular momentum. And so the disc naturally does that. And it rearranges the different regions. And what I'm showing you here is what we call the first mode. But as you go up in frequency, you'll have the second mode, the third mode, and this pattern will get more complex, and you'll see more nodal lines. You'll see it will cross the axis multiple times. But in every single case, it's automatically arranging itself so that these different regions, at least on axis, they perfectly cancel out. And that leads to the other really important characteristic of the BMR, is that it still has the piston output. So throughout the entire range of operation, you have the piston output, but then what happens is you superimpose on top of that the modal behavior. And we'll come on to that a little bit more detail in a moment. So just kind of, completing the story on this guy. So there's this ideal object, but the problem is that it needs a perfect force to drive it. And why is that? The moment you attach a real force, so something like a voice coil, this is how you get your force into your diaphragm. As soon as you attach that to the disc, you've added some mass, and the mass of that coil, it sort of destroys the natural behavior of the free disc, because the free disc now, again, it tries to rearrange itself, but now it's got this big chunky mass on the back at a certain location, and when it rearranges itself, now the areas are all kind of out of whack, and so you get a nasty looking response, which is what you see on the right hand side here, which is the brown color response, and that looks very, very much like cone breakup, and in a sense it is. And so this is where the disc has now become unbalanced. So what I'm going to show you next is really, and this is what BMR is all about, is that we essentially figured out how to rebalance the disc. So we know you have to add a certain amount of mass to get a force in, and essentially we give you a prescriptive way, of then rebalancing for the effect of adding that mass. Now this involves things like admittance functions and gets pretty in depth, but I will cut to the core of this. Essentially is that you can balance, so you have to consider the highest mode that you're going to encounter in band. So we do what's called an eigen mode analysis. Pick out the eigen frequencies. So that's where you look at the disc in a simulation package to see where the free modes of that disc are. And we go, okay, in band, there's 7 modes in band. That's maybe a little bit too much perhaps. So what we will do is we'll make the disc a little bit stiffer. So we'll make it thicker, or we'll change the material. Now we've got 4 modes in band. Perfect. That's exactly what we like. So now what we do is we attach our voice coil at a specific location, and then we attach some rings of balancing mass at some other specific locations to rebalance the disc. And that's what you see here on this image on the lower right hand side. So you can see this in the cross section here. You can see the voice coil being added at this location, and then you see these little rectangles or little squares. So in rotation, these would be rings. And these rings...
Are you implying the voice coil is not necessarily concentric?
Oh, no, the voice coil is concentric.
Oh, yeah, okay.
Most definitely. And again, that red dotted line shows the center of the disc.
Yeah, okay.
So it is fully concentric. And interestingly, one of the outer masses, we actually incorporate that into the landing of the roll surround, just to reduce having to add any unnecessary additional components. So what we do, we add these masses to the disc, and we rebalance the disc, and achieve all of the good stuff that I'm going to show you in a moment. Now, obviously, one of the elephant in the room question I have to answer, which everyone asks, is, you're adding mass to the diaphragm, so you must be killing the sensitivity. Well, to a certain point, you're absolutely correct. So what we tend to find is, for an equivalent like-for-like scenario, we might be about a dB, maybe worst case a dB and a half less sensitive on axis to a comparable size piston drive unit. However, you have to remember that we're not only interested these days in what happens on axis, we're interested in what happens off axis as well. And that's where what we call the efficiency becomes more into play, because your piston may be efficient, but only over a limited range. And then to achieve full range behavior with the wide directivity, if you cannot do that with a piston beyond a certain size, right? So then you go, okay, I have to add another drive unit. So I'm adding a lot more parts, a lot more, I have to add a crossover, potentially have to add a second amplifier channel. So then you go, well, actually, hang on a minute, I've gone from what was going to be, a single unit that I added a bit of mass to, and I lost about a dB on axis. But what I did is actually I preserved the off axis across the whole range, so that I can still just have a single drive unit. And really that's one of the real beauties of BMR, is that you can get this full range behavior that's largely decoupled from the size of the device. And so you don't have to have multiple drive units and crossovers and so on. I'll get to some really good examples of that in a moment. Just wanted to give you one last thing on the sciencey side, which is something I talked about earlier, which is this superposition effect, the fact that everything is additive. So what you can see on the left-hand side here are some modes, and this is looking at velocity and frequency. And so you see the red sort of triangle shape there, that's the piston mode. And then the blue one, let's say that's the first bending mode. And then the black one here, it's the second bending mode.
The y-axis velocity, using velocity because it's proportional to sound pressure?
No, so actually acceleration is proportional to sound pressure. We're using velocity because it's actually the way we typically look at modes. But yeah, you're absolutely right though. When we want to look at pressure, we need to convert it to acceleration.
Okay.
And to do so, you essentially multiply by the angular frequency. Again, we don't have to get into the details, but essentially you take these velocity profiles, you turn them into acceleration, and then you see this is what the output looks like from the speaker. And so you can see the piston output in red here, and it covers the whole range. Okay, maybe only on axis the whole range, but it contributes across the whole range. And then you have the modal output, and it adds in superposition, so it combines with the piston output. And then you have the second mode, and so the second mode adds on top of the first mode, which adds on top of the piston, and so all of it acts in superposition. And that's really part of the sort of the beauty of what's going on here. And you can see that when we look at what's called the directivity or the polar plot. And so you see here, this is for a 3.5 inch diaphragm. So you see here for the piston at low frequencies, you can see like the blue and the green curves here, nice 180 degrees of output. But as you go up in frequency, you start to see this lobing behavior, and really there's only strong output within a sort of a 40 degree window, perhaps 30 degree window. Contrasting that with the BMR, I'm just going to have to move my camera window here. On the right hand side here, you see for the BMR, you can sort of see that underlying structure of the piston, but superimposed upon it is the structure of the modal behavior. And so you can see it preserves the output off axis here much more effectively than the piston does. And this is bear in mind, this is a 3.5 inch size. So again, a 3.5 inch piston speaker is typically only useful up to probably about 2.5 kilohertz.
The piston driver diaphragm, you've got maybe like 3 or 4 curves that are quite circular, and then it goes into the highly modal thing. What frequency are we talking about there?
So this isn't going modal. This is purely to do with the power beaming.
Sorry, I don't mean modal. I mean directional.
Yes, the directional. So essentially the blue one is at 1 kilohertz. The green one is at 2.3 kilohertz. The red one here is at just under 4 kilohertz. So by 4 kilohertz, you are a good probably about 8 dB down over here.
Right.
And so even at 45 degrees, you're probably about 4 dB down or so there. So, but again, with the BMR, you see it preserves that output by combining the modal structure. And actually what we do is just where the piston component of the BMR, so just where the piston component would start to do its beaming, that's where we actually set the first mode. So we control the material properties of the disc and so on, so that our modes occur just at the right point, just where they need to. So just where the piston behavior starts to beam, that's where we add in the modal behavior. And just to give you some real world examples, let me minimize that for the moment. So this is a 2.5 inch BMR. And you can see here, very typical properties: 4 ohms DCR, 115 hertz free air resonant frequency. And this will do 86 dB at 1 watt, 1 meter. So actually very typical with a conventional driver, actually, of that size. Now, what's important to note here is that both of the frequency axes of these two graphs is going up to 40 kilohertz. So you can see 20 kilohertz on this left-hand side one is here. And then you've got another octave out here to 40 kilohertz. But what you see for the BMR across the whole band up to in the audio band is a flat on-axis sound pressure level. And then the blue curve is the sound power, which is that integration of all of the hemispherical output. And again, what you see is a very, very smooth, gradual roll-off, which is the kind of psychoacoustically desired shape of what it should look like. And you can kind of see that. This is on the right-hand side here, this is what we call a directivity contour plot. And so actually 0 degrees on axis is right up the middle here. And then you basically go to plus 90 at the top and minus 90 at the bottom. And again, this is going out to 40 kilohertz. And so you can sort of see how the piston would, a pure piston would sort of follow this very, very dark red region. And it would, and as you go up in frequency, it comes narrower and narrower and narrower, sort of into the on-axis position. And everything you see out here is being provided by the modal behavior. So that's all well and good. That's a 2.5 inch. What about a 3 inch? So then here we have a 3 inch, and again you can see the same sort of smooth sound power response in blue. This dip here, that's due to the finite baffle in our measurement chamber. This is an artificial effect from the measurement. Not to worry too much about that. And again, we can go up in size again. This is a 3.5 inch one actually. I'll show you the drive unit in a moment. But again, you can see up to 40 kilohertz. Again, very, very smooth sound power response. Lots and lots of wide off-axis output, meaning that, again, in room. So this is a 3.5 inch unit. Clearly, there's absolutely no need for a tweeter. Absolutely no need. In fact, I guarantee you this will outperform most tweeters in terms of providing off-axis output. And actually, we saw that with some people we're working with. We're developing a hi-fi tweeter for a pretty high-end company, and the directivity of some of our much larger BMRs actually was considerably better than this dedicated tweeter that was literally going to operate from 1 kilohertz upwards only. And we have our full range BMR drive units operating from 100 hertz or even a little bit lower sometimes, going all the way up. And in the case here, you can see going up to 40 kilohertz and beyond with that kind of wide directivity. So it's really something quite special.
Cool. Did you want to do a little show and tell, like, so we can see what these things look like?
Yeah,
I'll turn off the screen sharing now, so you can get get a better view of your mug.
So yeah, absolutely. Thanks, Dave. Let me pick out a few. So this is probably our smallest, certainly in diameter at the moment to date. This is what we call the BMR 28. So it's 28. The numbers that we use typically refer to the diameter of the disc that we use in here. So this guy actually is. Just put the calipers on it. Yeah, this is about 45. It's about 45 millimeters outer diameter. But again, this operates really nicely from about 100 hertz to beyond 20 kilohertz. Works quite well into the ultrasonic region with all of those BMR properties. Works great in. So we actually designed this one with quite a pokey motor. It's quite a powerful motor. So you can put this in a pretty small enclosure volume and have it with a port or a passive radiator, and it gives a really nice bass response. So that's one of the smaller.
Most of the drivers, are they all used in a chamber?
Oh, you mean with an enclosure?
Yeah, with an enclosure.
I mean, they don't have to be. I mean, that's how we design them, and that's how they're mostly used. There is probably a small subset of the very, very small hi-fi world that uses what we'd call kind of dipole speakers, where they actually have the no chamber on the back as well. And again, there are some different design constraints that you'd apply, particularly around the low frequency alignment side. That if you design something for that configuration, it wouldn't work very well in it when you put it into an enclosure. But yeah, there's nothing stopping you using it that way if you like.
Yep.
Yeah.
And what sort of applications you go into? Hi-fi stuff or smart speakers?
Yeah, I mean, this little guy here, and I was going to pull out one of the next ones up, is actually a square one. These guys, again, typically find these in compact smart speakers. You find them in Bluetooth products, portable products. Actually, the square one, you find this in a lot of sound bars. And conferencing devices as well for the smaller one. I wanted to show you something a little bit unusual. This is what we call a high aspect ratio panel, a HARP BMR, and this essentially is like taking a regular BMR. I have a bigger one here, and imagine taking like a one-dimensional slice across the middle here. That would give you a beam like that, and so this is almost like a one-dimensional BMR. Now this actual unit I'm holding in my hand here is a discontinued unit now, but we are just about to we're just starting prototyping our new range of HARP, the first of our new range of HARP drivers, and actually that unit is going to be about the width of a AA cell battery, and
wow.
That will be predominantly from speech upwards, so probably about 250 hertz upwards. But yeah, we're looking to expand that range as well. But it's something that's a little bit unusual.
So the new harps, would those be ready for customers in end of this year, or what's the kind of the timeline for the conference speakers, sound bars, probably automotive as well, and the suspension of the windshields, whatever that's called on the side of the
A pillars and B pillars.
A pillars, B pillars.
Yes, yeah. Again,
Tim's a car guy, so he knows this stuff.
I mean, that's obviously a natural location for something of that form factor. So in terms of timing, I mean, we're just kicking off the prototyping of our first design, and actually we've actually incorporated some new techniques into this that will kind of cause some of the challenges, let's say, in these very, very early. I mean, this design is probably 15 years old now. So we believe we've solved one of the key limitations of this guy, and all of our simulation suggests that it will work nicely. But until we actually build one, I won't be able to tell you for sure. But if it works as per our simulations, then yeah, we should be ready to start sampling, if not by the end of the year, early in 2021.
Okay, and I think like the summarize the commercial aspect, you touched on it, but in purchasing these for your product, it's really got to come from a system approach where you have to understand that you're reducing amplifier channel, reducing crossover cost, and reducing speaker count, and yeah, maybe more frivolous benefit, but reducing some tooling in terms of cutout for speakers. But definitely, so smart speakers, sound bars, automotive, and those are kind of some strong areas for you, and conferencing speakers. But I think one of the new areas we want to touch on this is.
Dave.
Yeah,
I just stop you. So just because, obviously, you mentioned the reasons to use a BMR from a system perspective, right? Minimizing cost and so on. But remember, if you were to use a conventional solution in place of a BMR, you typically would need two drivers, right? A mid-bass driver and a tweeter, and then you have a crossover. And then you have all the problems associated with the crossover. So it's not just the cost-saving side, but there is the performance benefit as well to that.
Right. So it's kind of the double whammy. We're always looking for price and performance balance. So this is kind of a double push, I guess. Yeah.
Yes. Sorry to interrupt you there.
No, that's fine. It's good to have some banter here. But after kind of where the BMRs have been for some time and really accelerating because of what you talked about with off-axis use of sound devices, whether it's smart speakers or smoke detectors, lots kind of interesting applications where you need to, and I think public address systems as well. Getting good sound distribution in a train station with a lot of noise bouncing around off of concrete in those buildings. Those are good applications for this stuff. But I think one thing we want to talk about is use in headphones. So this is a new area, and it's got some big wheels behind it in terms of like a big software company launched some headphones recently. What are they called? The Valve Index guys. Launched some, and this is a driver that was custom designed for them, but it's also available to the rest of the world with the right commercial discussions. But anyways, can you tell us a bit about the utility for using the BMR on these off-ear headphones?
Yeah, thanks, Dave. This is something I really quite passionate about, and it's a really interesting story. So yeah, absolutely. One of the engineers at Valve, one of the game sound designers at Valve, had this idea, looking at people using VR. And again, I'm in my 40s now. I'm not such a spring chicken anymore. But you look at like the young people today who are gaming, right, playing VR games, right. It's not 15 minutes, 30 minutes here or there. It's hours and hours continuously. And so, again, this is something that I didn't appreciate that until I started looking into this world. I had no idea people would play, VR for like 5 hours straight. But of course, when you do that and you've got all of this stuff on your head, right, you've got the display screens and you've got the, cables coming in and you've got headphones on as well. Essentially, you're blanketing the whole head with hot electronics. And so, firstly, from a long-term kind of comfort perspective, it's just hot and your head gets hot and sweaty and unpleasant. So one of the reasons for kind of trying to get away from like a headphone type solution was to try and free up, let some air circulate, let the heat out. But probably more important, or certainly I think more important from the direction they were coming from, the team at Valve, was how to improve the kind of in-game experience. And really that comes down to the human hearing mechanism, and actually it's so fundamental. It's so fundamental to our survival, or has been for certainly thousands of years ago. But it's very hard to fool it, and that's one of the big challenges in creating a virtual reality environment. There's so many challenges on the visual side. And they make better quality resolution, higher resolution screens, better color saturation, so on and so on. But the audio side's always been a challenge. And one of the big problems with headphones is that the sound is always inside your head. And one of the main reasons for that is because, the sound from the left headphone goes to your left ear and the sound from the right headphone goes to your right ear. But you contrast that with when you're listening to a pair of speakers, for example, in front of you. The sound from the left speaker goes to the left ear, but it also goes to the right ear. And same for the right speaker. The sound from the right speaker goes to your right ear, but a fair chunk of it also goes to your left ear. And that creates, some spatial perception. Combined with that is something called the head-related transfer function. So this is, again, quite a complex subject, but quite simple to think about. So when you think about how you let's even go back to survival, human survival. So the branch cracking in the forest as the T-Rex is stalking the plucky band of humans out hunting wild animals, right? You go, the branch, it was over there, so we run that way, right? So how do you know it's over there, right? So a number of things. So one of them is what's called time of flight. So again, if something occurs here in front of me, it's going to reach my one ear a little bit quicker than it reaches another ear. So again, my brain can go, oh, it arrived this ear a little bit before this ear. That means it's probably here. Coupled with the level difference as well. So because it's had to travel a little bit further to get to this ear, it's going to be a little bit quieter at this ear than it will be at this ear. Again, my brain can totally process that. But the third thing, again, which is really interesting, is what's called this head-related transfer function. And it's basically, since birth, you learn how the shape of your head and your ear structure changes sound waves as they impinge on your body. And essentially, you learn that structure and how it encodes. That structure gets encoded onto the waves that then go into your ear and get perceived by your brain. And so you can actually determine the direction of something from that as well. And actually, that's one of the most important mechanisms. And one of the problems is that everyone's head shape is different, and it's actually as unique as your fingerprint, probably more so. So, there's various mechanisms out there, things like binaural recordings. There's all the processing they can add to the game sound engines to try and, people wearing headphones to try and give them an out-of-head experience. But it's very computationally intensive to do that. It requires a lot of processing power, and even then it's never going to work that well for somebody because they're using an average model of an average human head, and of course, as I say, everyone's different. So what the team at Valve and specifically Emily, the engineer that we worked very closely with, her concept was, what if we could move the headphones off the ear so that they're sitting just off the ear, so that you capture some of that ear structure in the sound waves as they enter the ear. Actually, the way they're positioned ever so slightly tilted forwards. So again, you capture a little bit of that structure, but also it allows the heat to escape. And so, if you could solve this problem and have an off-ear solution that works, then it potentially would be great for VR gaming. The problem they had was that, again, because everyone's head shape is different and so on, every time they put the headset on a different user, the speaker unit would be positioned a little bit differently relative to their ear, right? And so what that does is, again, as we saw from some of the plots I showed you earlier, for a conventional speaker, a low frequency is not a problem. But at higher frequencies where you have this beaming effect, what happens is that the highest frequencies, sometimes you're going to miss them because of that slight misalignment of the speaker relative to the ear. And so the team at Valve, they tried a lot of different drive units and they weren't finding anything that was giving them that consistency. And then they bought some BMRs on the Parts Express, built them into a little headset, and found that it was so much more tolerant to the different head shapes and different positions because of that wide directivity, even at the highest frequencies. And so that's why Valve then approached us and said, hey, let's do a joint development on this, and yeah, one of the most exciting and fun projects I've ever worked on.
Cool, very cool. All right, well, that's you talked about 4 hours of gaming, so this has been over an hour of BMR. So,
oh, really? Sorry,
no, it's good, but I think this is a good start for people to get to know where BMRs are applicable in products. A lot of good detail on how the fundamentals of them help the performance, and then the system thing, as we discussed, can be economical to deploy in the market. So, Simon, do you want to ask any more questions?
I think we've covered it pretty well. It's going to take me a while to digest some of that anyways.
Yeah. All right. So yeah, I guess let's table it for today. Now, if everybody likes what we're doing, please subscribe to the channel. We're doing this every week. And so, of course, a big thanks to Tim Whitwell coming. It's Woodinville, Washington, I think, is the HQ for Tectonic in the Seattle region. So lots of exciting stuff coming from them. I think there's some big product announcements coming soon people can watch for. But yeah, so thanks, Tim, so much. We really appreciate your time today.
Thank you very much. Thank you both, Dave and Simon. I really enjoyed it. It was really interesting. So.
Okay, great. All right. So thank you again, Simon, and let's talk to you guys next week. Thank you.